Since late 2018, when the updated IEEE 1584 model was released, there's been a lot of dialogue in the industry regarding some of the limitations or some of the applications and some of the implications of using the model and comparing against studies that were previously done. Today we're going to be talking about some ways to kind of join that conversation. My name is Jim Chastain. I'm an applications engineer here at EasyPower, and we've titled this presentation for the next 30 or 45 minutes, Arc Flash Outside the IEEE Boundaries. And as we are in the habit of doing, we like to start each session with a poll question. And if you would please contribute to the dialogue by responding to some of these questions. When performing an arc flash study, how often have you used custom values for the working distance? And this is just one of the variables that's in the model that users have a control over or an influence of. And I'm curious how the audience has been able to navigate some of these requirements. So it looks like we have close to a quorum. Let's leave this open for another 5 seconds. Appreciate you joining us today. And by all means, if you've got questions or you want to contribute, use the question box in the webinar control block. So here's how folks have weighed in on this. Majority have not made modifications, and fairly, I'm surprised that there's as much management of that variable as we see. Good, thank you. All right, so let's tackle the second one. And that is, have you decided to use IEEE 1584-2018 on all your arc flash studies? Now again, this has been left up to the responsible party as far as whether or not to upgrade from the use of the previous standard. And there's been some reluctance in some areas to use the updated model for some of the same reasons that we're discussing here. So it looks like we have a quorum here. Here's how folks have weighed in. Looks like a majority have decided to go ahead and use it, but there's some reluctance on about 30% of the population. And then finally, how often do you encounter, at least when you're using EasyPower tools, the comment that the some variable is out of 1584 range? And in part, this discussion is reflective of some of the frustration people have with what that means, and we'll try to get into more discussion about specifically that. All right, let's leave this open for another 5 seconds. We appreciate your participation, and by all means, there's no right or wrong answer, and there's no liability to participating. So here's how folks have weighed into this. Seems like a few have not seen it, and you're going to see more of it here in a couple minutes. Thank you for participating. Okay, so just as a quick disclaimer, what we're discussing today is not an official EasyPower policy or recommendation. It's basically a description or a conversation on how to utilize EasyPower to better understand your system. And to that point, one of the paragraphs in the 1584 model, it's under paragraph 4.2, is there are alternative calculation methods for system parameters that fall outside the range of the model. However, no particular recommendation can be made because there are other application details such as bolted fault currents, voltage, gap length, operating frequency, number of phases, types of fault, etc., that the user is advised to properly research alternatives. So the question that I pose is, can the model be used to extrapolate instant energy when parameters are slightly outside the limits as prescribed by 1584? Frankly, this was brought up because if you look at the data on the original 1584 from 2002, the tests that they ran were limited to a maximum of 13.8 kV, and yet the model was recommended or had a scope that went out to 15,000 volts. So there was some extrapolation done during the development of the original model. Okay, without belaboring that, let's just kind of talk about some of these. So in 2002, they did recommend that outside the range, a Ralph-Lee method as a substitute or an alternative would be an alternative because a Ralph-Lee method, being a theoretical model, didn't have the baggage, if you will, of having to align with data. And to that point, to that time frame, it hadn't really been proved to be incorrect. In other words, it was always a conservative value, and it would be a good fallback if we ran out of steam on the 1584. Well, in the 2018 release, there's no recommendation on what to do. So that's kind of throws us into this discussion at various times during different studies. Now, on the lower limit, it's fairly easy to deal with because we do have several alternatives. And EasyPower includes most of these, or gives us the ability to access most of these. So I'm not going to spend much time on this, but this includes the ability to, on systems that are 240 volts or less, below 2000 amps, to limit or max either the calc time or some forced value that we know is a conservative estimate for these parts of the system. Or we could look up from ANSI C2 recommended categories. And in some cases, we have the ability to use single phase estimates. Okay, so that's all well and good. Now, the thing that throws a wrinkle in the whole discussion are these correction factors that have been used at various voltages within the range. And there's in some cases, there's rules which are providing discontinuity in the model itself. And these include, some of these factors include working distance, electrode gap, enclosure size, and electrode configuration. And to prove the point, here's an excerpt from 1584-2018 talking about working distances and minimum working distances, and enclosure size and dimensions. So these all end up being almost footnotes, but sometimes they'll cause issues in our calculation results. So I want to show you where this shows up in EasyPower. What I've done is I've developed for some reason, I have some reason to be concerned about the instant energy being calculated for this particular bus. So let's kind of get into EasyPower and talk about it. So what I've done is I want to create a system of scenarios that have different gap dimensions and see how it affects this particular calculation. Now I could have a problem with this, and my assumed values were giving me numbers that weren't acceptable, or I'm just concerned about somebody having to work on this and we're getting even low numbers. So there's more than one reason to be looking at that. But I've created scenarios that included dimensions outside the limit, inside the limit, and below the limit. And what I'm going to do is highlight this particular bus and run the scenario manager report capability just for that bus on those scenarios. So we're going to create a report and then see how things are being reported. Now we can see, now we're going to exclude base cases. It's a duplication of one of these other existing cases or scenarios. But when I have the gap set below the minimum limit, I get the comment out of IEEE range, but the tool still calculates instant energy for me. And if I'm lower than at the lower limit, again, I don't get an error. I don't get that comment. And if I'm somewhere in the middle of the limit, I get a calculation without the comment. And if I'm outside the upper limit, likewise I get. So what I'm trying to show here is this is a reason for the comment. I'm holding all other variables the same, and it's my gap that's causing me this comment. Now, I don't have a problem with instant energy necessarily, but if I did, or if I was concerned about this, I might want to go back and have a specific measurement, because during the data collection, I made some assumptions on what this dimension is. The point is, I'm trying to point out where these comments come from. Now we're going to look at the same thing for the higher voltage. This was a 480 volt bus. Now let's look at let's close this. Let's look at a 15 kV, I think it is. All right, so we have a 13.8 kV bus. We're going to select it. We have a number of scenarios built. Let's save it without zooming in. And so we have both inside the limit, outside the limit, and then middle points are various dimensions between the two. And the point, or the issue I found here when I run the scenario manager on that individual bus is I was getting responses that were giving me the comment that I didn't understand. And so again, this is a method to kind of deal with misunderstanding or lack of understanding. Here, what I'm seeing is that when I'm outside the dimension for that voltage, that I get the comment, but I still get an instant energy calculation. Likewise, when I'm outside the limit, more calculations. If I'm right inside the limit between the high and the low, I don't get the error, but I do get calculations. What concerned me, though, was I'm inside the boundary, inside the band of allowable dimensions, but on some of these, I'm still getting the comment of outside the range. So that makes me wonder where I'm going wrong. Well, as I go back to the EasyPower Help system, I find that if I go in and look at the IEEE 1584 range under the EasyPower Help system, that indeed there's an enclosure width rule that says the gap has to be greater than, or the dimension of enclosure width has to be greater than 4 times the gap. So on some of the larger gaps, if my width wasn't adequate, it would give me a calculation, but it would give me that error at the same time. So again, Scenario Manager is a good way to deal with some of those issues. Now, when we look at overall application of the 1584 2018 model, we've known all along that there's some dipsy-doodle in it, and that it has a limit on not exceeding certain current ranges. In high voltage, it's limited to 65,000 amps, and in low voltage, it's limited to 106,000 amps. And that's because the model actually noses over and goes down to 0 at some higher current. And so we've extrapolated in general terms the 2002 version and the 2018 version, and it's a less conservative model at the lower voltages, and in some respects, it looks like in general. Now, after attending several IEEE committee presenters and papers, one of the common reports or common comments that is made is don't necessarily take the most conservative approach when utilizing the models. And so that kind of gives rise to, well, where does it make sense to kind of slice things a little closer as far as being conservative? And so what I'm taking a point or taking an approach is that by holding all the other variables constant, how do different parameters affect incident energy versus the voltage? And we see it's pretty linear. What we're comparing is the configurations of the closed enclosure, the buses. So there's vertical in a closed box, vertical terminated in a barrier in a closed box, and horizontal in a closed box. So they are, and a vertical in a closed box is the least disruptive, least hazardous. Terminated in a barrier is more hazardous, and then horizontal in a closed box is most. Now, a little side note, horizontal doesn't mean that the bus itself runs horizontally. It means the bus stub, or the end of the bus, is pointing out of the box in the vicinity of the head or thorax of the technician. And so consequently, it's considered most hazardous. But the point I'm getting at is that we have reason to believe that it stays fairly linear in terms of incident energy and voltage. Likewise, in enclosed configurations, while it's not totally linear, on a small stepwise change, it is continuous, and it's not linear, but it's close to linear in these ranges. So let's look at how we deal with this in EasyPower. So we've got a couple examples set up where I'm keeping the voltage the same, and I'm looking at a current variation, both just 10% below the limit and then 10%, 20% above the limit. So let's see how this works. So let's close this. And we can close this. And we're going to open up 480 volt over current range. So again, basically we have 4 independent sources of varying degrees of current, and what we want to see is the calculations, what the options are, and the results are with the different methods that EasyPower shows us. So if we go into short circuit, look at fault current, and fault all the buses, we can see that they match the sources that were being shown. If we calculate incident energy, we see that we have a continuous, fairly close separation between just below the boundary or just below the limit and right at the limit, and it's fairly routine. Now these, because they're outside the limit, if we look at our arc flash, we see we're getting the comet outside the range for these 2 buses. And if we look at our short circuit options, arc flash hazard tab, we can see under the advanced tab that we're applying the IEEE 1584. We're essentially just extending the calculation up, and even though it's not recommended, it seems like a reasonable thing to do. Let's look at what Ralph Lee would do for us. And so if we apply the Ralph Lee equations and fault all the buses, we get still a relatively small differential. And so I'm feeling comfortable using the calculations when I'm slightly beyond the limit for both a 10% difference and a 20% difference. It's just me. So let's try holding a higher voltage, doing the current range at a higher voltage. So I want to go to the start page. I want to go to 15 kV over current. Same type of setup. Now we're working on 15 kV. We're just at the upper limit, and we're looking at the voltage. Now these are open air, so that way roughly, or we can use the NESIC table lookup as well. So I take that back. Switch gear. Yeah, we use upper air on the higher one. Okay, so these are all classified as switch gear. Let's go to short circuit, fault all the buses, arrange for arc flash. Now here we see relatively modest incident energy for just below the limit and then right at the limit, and then a very high estimate for a 10% over or 20% over. If we go in and see how we've got this set up on advanced, we're seeing we're applying the Raffli method. So this is what I meant by Raffli is conservative. It's acknowledged to be conservative in this case. Looks like an order of magnitude higher, but it hasn't been proven wrong, and that's probably the reason. Will the tool allow us to apply it? It says, well, it's not intended for this range, so it's not recommended, but let's see what happens when we do it. All right, we get what we would expect as far as extending that calculation out. It looks like for a 10% change in the current, I have about a 10% change in incident energy. Likewise, I have the same thing if I go 10 and 20% above. So there seems to be some rationale in extending the use of the IEEE 1584 model, even though it's not recommended. Okay, I can tell I'm having more fun of this than you guys, but hang in there. Okay, so that was looking at overcurrent at the low voltage and then overcurrent at high voltage. Same is true with open air configurations. If we look at voltage versus incident energy, this is the open bus thing I was going for. We see we're fairly linear. We have a large variation at low voltages and more of a linear response between horizontal and vertical in open air. And likewise for both at fault current and incident energy, they actually approach the same values, and it looks like it's predictable. There's not discontinuity in the particular length and the particular results. So let's look at this in EasyPower. And if I go back to EasyPower, and let's go ahead and close this guy. And then open. So this is open enclosure or open air. We're at 14 kV, so we're right at the limit. We're going to be just under, right at the limit, and just over the limit. And we're going to have 65 kiloamps, which is right at the upper limit for medium voltage. So let's see what our short circuit results are. And again, it's more that the methodology that I'm emphasizing here. It's not the results. So we see a modest increase when we get a 10% difference in voltage below the limit, and we have, although it's higher, we have a modest difference between the 20% and the 10%. And so if we look at how this has been calculated, right now I'm comparing this to the annex single line to ground. Now this I want to talk about. So this is, we've actually done webinars on this for an open air single line to ground over 15,000 volts. This is a NESIC lookup table. And what we're seeing is a multiplier of 1.5. If we're not comfortable with that, we can change the multiplier for a three-phase fault. And so if you've followed my presentations before, that application is actually meant for a single phase comparison, and at 15,000 volts we get what would be considered a rational comparison between the limit and 10% and 20% above for a single line to ground. If we compare that against a three-phase limit, then it's using that multiplier, and we're getting 3 times that. So in my mind, there's some justification for utilizing this calculation with something just slightly higher than the single phase, single line to ground. If you followed all of that, they might be really helpful. If you've got questions about how I did it, that's okay too. Be happy to either deal with it now or take it offline. And my point is that it seems reasonable to apply a small differential in one parameter and extrapolate the given calculations to, even if it's outside the range of the 1584 model. My question is, what do you think about that whole approach? So we got a couple minutes. Let me kind of see what questions we've got. And one says it's not related to today's topic, so I may take that one offline. Be happy to do that. Again, it's Chuck's asking, why does a barrier create a higher instant energy? Okay, so the whole discussion about gap orientation, bus electrode orientation, has to do with the butt end of the bus itself. Whether it's terminated or whether it's open, whether it's inside the cabinet or whether it's pointing outside the cabinet. And it's been proven in the 2,000 some odd tests that they've done is that when an arc is initiated, it travels to the end of the bus, and then the ion or the plasma bloom pattern goes straight out from the end of the bus itself. Now, when you have a terminated barrier where there's no ability for the bloom pattern to go straight out from the butt, it goes out horizontally in the plane of the termination barrier. So the example that they show is buswork that's terminated into a molded case circuit breaker, which is an insulated barrier, and so the bloom pattern goes straight out from the arc at that point, straight out being perpendicular to the bus. So that's why barrier instant energy created in the barrier is higher than for a non-terminated electrode. The thing to really consider is the difference between horizontal in a closed box and vertical in a closed box. It has nothing to do with the direction of the bus itself. In other words, if I have 3 horizontal buses running horizontally and they do not have a termination that points out at the operator, then that should be classified as vertical in a closed box. If I have, and the example that they give in the standard is the most obvious example, they say, of horizontal in a closed box, and that is when you have a low voltage power circuit breaker racked and it's outside of the connectors behind it, but it's still sitting in the enclosure itself. The place where it left the bus, the place where it was terminated, that's going to be a horizontal in a closed box. But the model doesn't take into account you have these other elements that are blocking the discharge, and so that's another reason to consider use of the model in your particular application. Okay, well, Mike's got a question that I'll answer via email, and it looks like we don't have any others. Appreciate everyone joining today. Hope it's been useful as far as asking some questions and maybe something you can apply relative to your own experience and use of the tools. Be sure to check the website. We do have monthly ARC Flash workshops. We do have live online regional training. It looks like we'll probably be scheduling in-person regional training in the second half of the year. And we're adding a dozen of video recordings on various topics. Thank you for attending today and have a good week. So long.